Kia ora team and welcome to another online tutorial. Today we're going to be talking about Phasor circles. So mainly we're going to be talking about what they are, that's maybe new and confusing to some people, as well as what we use them for. Velocity and acceleration of an object moving in simple harmonic motion are constantly changing, as we've talked about with both our simple pendulum and a mass on a spring. Our forces are proportional to displacement or extension, making predictions difficult and specific calculations difficult. However, if we model the motion of an object in SHM as circular, and we use a reference circle or Phasor circle, then our model would have a constant rotational velocity. Okay. With that, we can do calculations on instantaneous velocity and acceleration, which we otherwise wouldn't be able to. We're going to look at three Phasor circles here, how they match up our understanding of pendulums or masses on a spring for SHM. If we look at a graph of displacement and its relative Phasor circle, okay, we can see that if our Phasor circle, as convention, moves anti-clockwise, that displacement from equilibrium, remember that we always measure from equilibrium, will match up to the vertical component of a radius of our Phasor circle, of which that vertical component of that radius will be equivalent to our displacement. Now, this isn't just for displacement. We can do this with velocity and with acceleration. We can use equations to calculate displacement, velocity, and acceleration relating to these, but we'll talk about these in another video. We can also graph velocity and acceleration of object with SHM, okay, in the same manner, as well as acceleration. Noting that our velocity and acceleration are 90 degrees out of phase, meaning that when our velocity is at its greatest, okay, our acceleration is at its minimum, and vice versa. That's what a Phasor circle is. That's how we use them. We'll go into depth around calculations in another video, but our main takeaways from this are Phasor circles rotate counterclockwise, that the vertical component of the radius represents what we're modeling. And a reminder that velocity and acceleration are 90 degrees out of phase. Okay, as we can see above, when we're at our maximum for velocity, we're at our minimum for acceleration, and vice versa at any point which we mark. Things we can take away from Phasor circles or observing our Phasor circles for SHM are, and this is in line with our understanding of simple pendulums and masses on a spring, when our displacement equals 0, when our displacement is 0, our velocity is greatest. Okay. When our velocity is at its minimum, displacement is at its greatest, and acceleration is at its greatest too. And last but not least, when our displacement is at its maximum, there is no velocity, but our acceleration is at its greatest. Okay. So greatest displacement, minimum velocity, greatest or maximum acceleration. We've used D here being our displacement Y. Hopefully that's explained why we use Phasor circles, as well as some of the observations we can make inherently from Phasor circles looking at displacement, velocity, and acceleration. Hopefully that helps you get out there and get into some physics, team. Good luck.